In this problem, we build on the prior couple of problems that have looked at the distributed force along a spinning blade and the internal force along this spinning blade. We're now going to build on our calculations for the internal force within the blade, as you see here, so you can look at the previous videos if you like and think about what the maximum axial stress is along this blade. Well, axial stress is just going to be the force divided by cross-sectional area. Okay? And so where the force is a maximum, we expect the axial stress to be a maximum. Now, where is that going to be? Well, let's think about what's happening with this problem. If we're at the outer part of the blade, there's no distributed force, or there's no length over which a distributed force might be acting. And so the internal P, this is external, and this is internal, is going to be 0. But as we move from right to left, and x is getting larger and larger, meaning that we're getting closer and closer to the center of rotation, we see that this external distributed force is going to be acting over a longer and longer section. And so the force P has to also be getting larger and larger and larger. So just by kind of thinking through things, we can say that the maximum stress is going to be where x is equal to L at the center of this spinning system. And that might be a little bit counterintuitive because you're like, oh, the velocity is a little bit smaller there. True, but the force is building up. The internal force is building up based on the length of that's beyond. That's having to undergo this acceleration. Another thing to point out at this point is that we defined x to be 0 when it's out at the outer blade. And if you look at our free body diagram here, you can see that there are only two forces that are acting against each other. I mean, the integration of this distributed force and P, the internal force. What would have happened if we had said we want x to be 0 at the middle? Well, then we would have had this maximum force, okay, acting at the middle as an external force. We would have had another internal force, P, still there, and we would have had this distributed force acting on the blade as well. The point is there would be 3 variables that we're keeping track of. We'd have to know what this reaction force is at the middle, we'd have to know P, and we'd have to know the force F from the distributive force, the integral of this distributive force. So it would have made the problem a little bit more complicated in that we have to keep track of this reaction force at the middle. But now we've essentially solved for that going from the outside coming in. And what we do here for that calculation is we plug in x equals L if we're trying to figure out force. If we're trying to figure out stress, we just plug in the x equals L, and we get 1/2 L squared here in these parentheses. And I need to also divide by area, right? Because that's what this axial stress is. And so this term right here goes away. Let's go ahead and calculate this out using Colab. Now, we already have a calculation here for the force. We can just go ahead and build on it by well, saying that we're going to calculate a max stress, so sigma max, and that's going to be at P divided by A, which just is going to be, well, if I do it here, I can do it like that, all right? This would also be equal to rho omega squared times quantity 1/2, or just 1/2 L squared. But what do I need to do? I need to change where my x is if I'm going to do this. My x is not at L over 2, it's at L, okay? And we're dividing by this area, A, that's fine, but I don't know what my values might be in this problem. They could have changed. So let's see, area is 2.8, so let's change that. Omega is now 95. Density stayed at 1,000. Okay, the length is 1 right here, 1.0, so I'll change that as well. Okay, I think I've changed the parameters appropriately, including the fact that we're interested at where it's maximum. When x is equal to L, we're going to calculate the P, and then we're just divide by A. Okay, so that might be, kind of, I don't know, it's not exactly this equation, but this is how we can change our existing code to get us an answer that seems to make sense. So here we'll say is equal to, and this is going to be, okay, so they wanted units. We want units of megapascal. All right, so we're going to multiply by 1 e to the minus 6. So we have a sigma max here times 1 e minus 6. 1 decimal point will be plenty, and we do megapascals like this. All right, let's see what we get. Great. Okay, so our P changed and it's higher. Well, I mean, a lot of variables changed, so I guess it's not necessarily apples to apples, but we do expect that the P, the internal force, is going to be higher, at x equals L at the middle than, say, at halfway along the blade. And we've been able to calculate stress just by dividing that P by the cross-sectional area. And we get 4.5 megapascals. Well, I hope you found this example useful. Thank you.